The problem is R is a commutative ring with unity, and we've got n elements, A1 through AN, from the ring. I is defined to be this set, which, analogous to linear algebra, you could think of as a set of linear combinations, though the coefficients of the A's are not scalars from the real numbers, for example, but they are from the ring itself. So it's a similar concept to linear combinations, but not the exact same thing. Likewise, because of that, this notation here is a similar idea as spanning set of vectors in linear algebra, but not quite exactly the same idea. Our goal is to prove I is an ideal in R, and I'm not going to do the full proof, but just the idea of the proof, maybe should I call it the ideal of the proof? Okay, that L is only there for fun. It's the idea of the proof. Okay, so you'd want to use the ideal test. Use the ideal test. So what does that mean? That means, well, first of all, you should verify that it's non-empty, but it's obviously non-empty. Obviously, I is not the empty set. It's got the A's in it, if nothing else, where you could take the R's to be 1, for example. Is it closer to subtraction? If it is, that would verify that it's a subgroup of R if you only focus on the group structure, which is necessary to be a subring. And is it superclosed under multiplication, more than just for a subring, but an ideal? So for closure under subtraction, and again, I'm not going to write sentences. That's just why this is the idea of the proof. Write 2 arbitrary elements in this set. There is 1 arbitrary element. Subtract another. How should I make the notation different? Well, you could, for example, use prime notation on the R's, for example. Nothing to do with derivatives there, just different notation. These 2 linear combinations, if you will, would represent 2 arbitrary elements of I. And addition, meaning subtraction, subtraction as adding additive inverses is commutative. You can rearrange things, use the distributive property. Ultimately, you can factor out the A's out of each term. You get R1 plus R1 prime times A1 plus R2 plus R2 prime times A2, etc. Oops, with minus signs, sorry. Through Rn minus Rn prime times An. And each of these things, since a ring is a group under addition, and therefore, again, with subtraction, you're still going to have closure because subtraction means adding additive inverses. These are in R. Okay, so it's in the right form. It's in the form of a linear combination of A1 through AN. So this is an I. That verifies closure under subtraction. Superclosure under multiplication. Give me an arbitrary element R of the ring and multiply it times an arbitrary element of I. Use the distributive property and the associative property, maybe for extra emphasis. And once again, because of closure in R, each of these things is in R. Therefore, you have a linear combination, so to speak, of the elements A1 through AN. This, by definition, is an I as well. There we verified superclosure. That does it. Praise the Lord, we're done. If you've got more than one A here, it's no longer what we call the principal ideal, seemingly. Right? What is principal ideal? Recall that a principal ideal is generated by just one element, one generator, so to speak. In group and ring theory, we use the word generator. In vector space theory, we use the word basis or spanning set, if we're not talking about linear independence. So it seemingly is not a principal ideal because we got more than one element if n is greater than 1 here. However, little word of warning, it could be a principal ideal still. It's possible that we could find some other element, call it B. This could equal the principal ideal generated by some individual element. That's possible. Okay. So just realize that going forward, sometimes ideals that are in this form that don't look like they're principal ideals could equal the principal ideal generated by some element.